Example 14.7. Why are silicon and gallium arsenide are preferred materials for solar cells? Now see, actually solar cell convert radiation energy, or we can say radiant energy, into electrical energy. Okay. Now see, suppose we carry out the study related to the intensity of the solar radiation with different energies which incident at the surface of the earth. Then we can observe this thing, the radiant energy which one is incidenting on the surface of the earth from the sun. In that particular radiant energy, the maximum intensity of the radiations, that is with 1.5 electron volt energy. It implies that now if we use the solar cells, or we make the solar cells with the material which have the band gap energy that is less than 1.5 electron volt or near about 1.5 electron volt, and for silicon band gap energy that is 1.1 electron volt, and gallium arsenide is 1.53 electron volt, and therefore these materials are more preferred to develop the solar cells. Clear to all of you? Now example 14.8. Justify the output waveform of the OR gate for the following inputs A and B given in figure. So here see, the inputs are given to you for A and B, and now we have to justify the outputs. Okay. Now here આમાં અહીંયા પર T1 ને T2 ને લખવાનું રહી ગયેલું છે, right? હું read કરું છું. Okay. So for the time T1 less than T, here first A is 0, B is 0, so output is 0. Then for the time T1 to T2, A is 1, B is 0, so output that is 1. So this one is OR gate, so we know this thing for OR gate, if all the inputs are absent, then and then only the output is absent. In any other case, we will get output. Okay. So T2 to T3, A is 1, B is 1, so output 1. T3 to T4, A is 0, but B is 1, so output is 1. Then after T4 to T5, A is 0, B is 0, both 0, 0, right? And therefore output that is 0. Then after T5 to T6, A is 1, B is 0, and output is 1. Then T6 onwards, A is 0, B is 1, obviously output is 1. Clear to all of you? Then after, see, take A and B input waveform similar to that in example 14.11. Sketch the output waveform obtained from AND gate. Now see, for AND gate we know this thing, if all the inputs are present, then and then only we will get output. In any other case, we will not get output. So see here, A and B both are 0, 0, so output is 0. So we have to prepare the waveform for output. So up to T1 the output is 0. Then T1 to T2, A is 1, B is 0. Obviously output is 0. So T1 to T2, see here, 0. Then after T2 to T3, both A and B are 1, 1. So output is 1. So T2 to T3, output 1. Clear? Then T3 to T4, A is 0, B is 1, hence Y equal to 0. So T3 to T4, Y is 0. Then T4 to T5, A 0, B 0, so Y 0. T4, T5, this 0 level. Then T5 to T6, A1 but B 0, again output is 0. So T5 to T6, again 0. Then T greater than T6, A is 0, B is 1, again output is 0. So after T6, again you will get output 0. Clear to all of you? Any doubt in this? Then after 14.10, sketch the output Y from a NAND gate having inputs A and B given below. Now see, here A and B inputs are given to you. Corresponding output will be what? And as per that output, we have to prepare the waveform here. Now, NAND gate. So, when AND gate is followed by NOT gate, we get NAND gate. Now, the working of AND gate is like this. If all the inputs are present, then and then only we get output. In any other case, we will not get output. And opposite to it, the working that is of NAND gate. So if all the inputs are present, then we will not get output. In any other case, we will get output. So see here. For time t less than t1, A is 1, B is 1. See here in the waveform. A is 1, B is 1. A higher level बताया. So output is 0. Then A is 0, B is 0, we will get output. A0, B1, we will get output. A1, B0, we will get output. Again here, A1, B1, so both the inputs are present, we will not get output. Then A0, B0, again we will get output. A0, B1, again we will get output. Clear to all of you? Now exercise example 1, 14.1. In an N-type silicon, which of the following statement is true? A. Electrons are majority charge carriers and trivalent atoms are dopants. Wrong one. B. Electrons are minority carriers and pentavalent atoms are the dopants. Again, wrong one. C. Holes are minority charge carriers and pentavalent atoms are dopant. Yes, that is true one. D. Holes are majority charge carriers and trivalent atoms are the dopants. Again, wrong one. Then in p-type silicon, which of the following statement is true? A. Electrons are majority carriers and trivalent atoms are the dopants. So again, wrong one. Electrons are minority carriers and pentavalent atoms are dopant. Again, wrong one. See, holes are minority carriers and pentavalent atoms are dopants. Wrong one. This one is for N-type. Then D, holes are majority carriers. Yes. And trivalent atoms are dopant. Yes. It implies that the D option is correct one. Clear? Example 14.3. Carbon, silicon, and germanium have 4 valence electrons each. These are characterized by valence and conduction bands separated by energy band gap, respectively equal to Eg of C, Eg of Si, and Eg of Ge. Which of the following statement is true? So we already discussed one illustration of this type. We know this thing, the maximum band gap energy, that is off. carbon, then less than that, that is of silicon, and then less than that of germanium. So option C, that is correct one. Clear? Then 14.4. In an unbiased junction, holes diffuse from the region to region A. Free electrons in the region attract them. B. They move across the junction by the potential difference. Holes concentration in P region is more as compared to N region. And D. All the above. So option C, that is correct one. Now next 14.5. When a forward bias is applied to PN junction, it A. Raise the potential barrier, B. Reduces the majority carrier current to zero, C. Lowers the potential barrier, D. None of the above. So option C, that is correct one, lowers the potential barrier. And in theory, we already studied this thing. Clear? 14.6. In half wave rectification, what is the output frequency if the input frequency is 50 Hz? What is the output frequency of the full wave rectifier for the same input frequency? So in half wave rectification, during the whole input cycle, we are getting only output when positive half cycle is there. During negative half cycle, we are not getting output. It implies that in output, we will get only 50 pulses. So frequency for half wave rectifier, that is 50 Hz in output. But if we think about full wave rectifier, then in full wave rectification, during input positive and negative both half cycles, we are getting output pulse. It implies that we will get total 100 output pulses for full wave rectifier. So we can say the frequency for full wave rectifier in output, that is 100 Hertz. Then example 14.7. A photodiode is fabricated from a semiconductor with band gap of 2.8 electron volt. Can it detect a wavelength of 6000 nanometer? Now see, we know this thing. In photodiode, to detect the radiation, the incident energy of the radiation, that should be greater than or equal to band gap energy. Now here the band gap energy that is given to you, 2.8 electron volt. Now the incident radiation, that is with wavelength 6000 nanometer. So what is the energy of that incident radiation? That first of all we have to calculate. So energy of the incident radiation, that is hc upon lambda. H, that is Planck constant, C, that is speed of light. So substitute all the values, 6.6 into 10 raised to minus 34 into 3 into 10 raised to 8 upon lambda, that is 6000 nanometer. So 6000 into 10 raised to minus 9 meter. Now if you solve this one, your answer will come to 3.3 into 10 raised to minus 20 joule. Now we have to convert this one into electron volt. So divide this by 1.6 into 10 raised to minus 19. Then our answer will be 0.2 electron volt. But see here, 0.2 electron volt, that is very much less than 2.8 electron volt. It implies that this particular radiation incidenting on the photodiode, that will not be detected by photodiode. Clear to all of you?
Yes.
Now see, example 14.8. The number of silicon atoms per meter cube is 5 into 10 raised to 28. This is doped simultaneously with 5 into 10 raised to 22 atoms per meter cube of arsenic and 5 into 10 raised to 20 per meter cube atoms of indium. Calculate the number of electrons and holes given that Ni equal to 1.5 into 10 raised to 16 per meter cube. Is the material N type or P type? Now see number density of electrons. So here when arsenic is doped, so 5 into 10 raised to 22 arsenic atoms are doped, it implies that 5 into 10 raised to 22 free electrons are available per meter cube. But when 5 into 10 raised to 20 atoms of indium are doped, so each indium will give you one hole. So 5 into 10 raised to 22 free electrons are there and 5 into 20 free holes are there. So electrons will combine with holes and therefore resultantly the number density of electrons obtained will be 5 into 10 raised to 22 minus 5 into 10 raised to 20. So resultantly we can write this one as, see this 5 that we can write 0.05 into 10 raised to 22. So we can take 10 raised to 22 common into bracket 5 minus 0.05. So number density of electrons, that is 4.95 into 10 raised to 22 per meter cube. Now Ni that is given to you, Ne is calculated. So we have Ni square, that is NeNH. So we can write NH that is equal to Ni square upon Ne. Ni square, so that is 1.5 into 10 raised to 16 whole square upon 4.95 into 10 raised to 22. If we solve this one, our answer will be 4.54 into 10 raised to 9 per meter cube. It implies that here number density of electron that is very much greater than number density of holes. So this particular semiconductor will be N-type semiconductor. Clear to all of you? 14.9. In an intrinsic semiconductor, the energy gap Eg is 1.2 electron volt. Its whole mobility is much smaller than electron mobility and independent of temperature. What is the ratio between conductivity at 600 Kelvin and that at 300 Kelvin? Assume that the temperature dependence of intrinsic carrier concentration Ni is given by Ni equal to N0 exponential minus Eg upon 2 kBt, where N0 is a constant. Now see, Eg that is given to you 1.2 electron volt, temperature T1 600 Kelvin, T2 that is 300 Kelvin. Now conductivity. So conductivity, resultant conductivity, that is conductivity due to electrons as well as conductivity due to holes. So in chapter of third chapter, we studied about mobility and we discussed this thing, the conductivity that is equal to mu E N E into E. Mu E that is mobility, Ne that is number density, and E that is charge of electron. So this is the mobility of electron, number density of electron, charge of electron. That will give you the conductivity due to electrons. And mu h, that is the mobility of holes, nh, number density of holes, into E, that will give you the conductivity due to holes. It implies that the resultant conductivity, that is E into this one. But we know this thing for intrinsic semiconductor, Ne equal to Nh, that is equal to Ni. So we can write E into mu E Ni plus mu H Ni. So resultantly, we can write E Ni into mu E plus mu H. But here it is given to you the mobility of holes is very much small compared to mobility of electrons. So here mobility of holes, this one is neglected. So we can write sigma, the conductivity, that is E Ni mu E. So we can write now this Ni, that is equal to N0 exponential minus Eg upon 2 kBt here in this equation. So sigma, that is E N0 mu E exponential minus Eg upon 2 kBt. So at temperature T1 you can write conductivity sigma 1 by this equation E N0 mu E exponential minus Eg upon 2 kBt1. For another temperature T2, you can write the equation for the conductivity sigma 2, that is E N0 mu E exponential minus Eg upon 2 kBt2. Now we have to find the ratio. So ratio of these two conductivities, sigma 1 to sigma 2. So E N0 mu E will be cancelled. Exponential minus Eg upon 2 kb T1 divided by exponential minus Eg upon 2 kb T2. And now take this denominator in numerator, and then you can write exponential this plus this. And then by taking Eg upon 2 kBt common, you can solve it. Substitute the value of kb in terms of electron volt upon Kelvin, that is this one. So directly you can substitute value of Eg here, that is 1.2, and then solve it, we'll get the answer. Clear to all of you? 14.10. In a PN junction diode, the current I can be expressed as I equal to I0 exponential EV upon 2 kBt minus 1, where I0 is called the reverse saturation current. V is the voltage across the diode and is positive for forward bias and negative for reverse bias. And I is the current through the diode. Kb is Boltzmann constant, 8.6 into 10 raised to minus 5 electron volt upon Kelvin, and T is the absolute temperature. If for a given diode I0 equal to 5 into 10 raised to minus 12 ampere and T equal to 300 Kelvin, then A, what will be the forward current at the forward voltage of 0.6 volt? B, what will be the increase in the current if the voltage across the diode is increased to 0.7 volt? What is the dynamic resistance? And D, what will be the current if the reverse bias voltage changes from 1 volt to 2 volt? Okay. Now see, first we have to calculate the forward current for forward voltage 0.6 volt. So take V equal to 0.6 volt. First calculate EV upon kBt. Okay. So substitute the value of E V.6 kb 8.6. See, that is given to you in terms of EV upon K. So we have to convert it in joule per Kelvin. So we have to multiply it by 1.6 into 10 raised to minus 19. That 10 raised to minus 19 and 10 raised to minus 4. So directly we can write that is 10 raised to minus 24. Temperature, that is 300. When you solve this one, your answer will be 23.26. Clear? Then after I equal to I0 into equal to cardinal exponential EV upon kBt minus 1, substitute the values and then solve it. Finally, you will get the answer, that is 0.06293 ampere. Then after, in second question, take V, that is 0.7 volt. Again calculate EV upon kBt, substitute these values in the equation and again calculate the current. Okay. And then we have to calculate the change in current, means increase in current. So previous current we calculated for zero point 0.6 volt. This current we calculated for 0.7 volt. And now take the difference of these two, we will get increase in the current. Now we have to calculate the dynamic resistance. So that is delta V by delta I. Delta V, that is 0.7 minus 0.6, that is 0.1 volt. Delta I, increase in the current, we already calculated here. So now take the ratio delta V to delta I and you will get the dynamic resistance. Then D. Now see, for both the voltages, the current I will be almost equal to I0 because that is reverse saturation current. Clear? And in case of more voltage, immediately you will get the reverse saturation current. So your I, that will be I0, but here negative sign is introduced because that is reverse bias current. So that is reverse saturation current. Clear to all of you? 14.11. You are given two circuits as shown in the figure. So that circuit A act as OR gate while the circuit B act as AND gate. Now see, take circuit 1. So in that first is NOR gate, then output of NOR gate, that is the input of NOT gate. And finally you are getting the output of your circuit. Now see here, actually NOR gate is made by OR plus NOT. So suppose first we think about the inputs A, B. The combinations are 0, 0, 0, 1, 1, 0, 1, 1. Then in NOR gate first is OR. So take the output of OR. That is 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Then it is followed by NOT. So not A or B, 0 to 1, 1 to 0, 1 to 0, 1 to 0. Now output of NOR, that is this one. Now that is input of NOT. So NOT will invert it. So now resultant output given by this NOT, that is 1 to 0, 0 to 1, 0 to 1, 0 to 1. Clear? હવે આપણે તો આ ઇન્ટરમીડિયેટ સ્ટેપ અન્ડરસ્ટેન્ડિંગ માટે લીધા. Now actual circuit નો આપણે વિચાર કરીએ તો A, B inputs and Y output. So see, 0, 0 and this output 0. 0, 1, output 1. 1, 0, output 1. 1, 1, output 1. It implies that when all the inputs are absent, then and then only the output is absent. In any other case, we are getting output. It implies that either A or B or both the inputs are present, we are getting output. So this is the working of OR gate. Clear? Now consider second circuit. See, in second circuit, A and B are first inputs of NOT gate, then output of NOT are the inputs of NOR gate. Okay, so let's consider first A and B, 0, 0, 0, 1, 1, 0, 1, 1. Now here both these NOT gates will give you the outputs. So here first one, A to not A, that is 0 to 1, 0 to 1, 1 to 0, 1 to 0. Then for B, 0 to 1, 1 to 0, 0 to 1, 1 to 0. Clear? Now these two inputs are of first OR gate. So we will get here not A plus not B. So 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0. But in NOR gate, after OR there is NOT gate. So we can say this particular one, this one, that is the input of NOT gate. So now NOT will invert it. So 1 to 0, 1 to 0, 1 to 0, 0 to 1. Now forget about this intermediate step. Think about only input and final output. So now 0, 0, this 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So see the working. If all the inputs are present, then and then only we are getting output. In any other case, we are not getting output. It implies that either A or B or both are absent, we are not getting output. So this is the working of AND gate. It implies that this particular circuit given to you in figure B that behave as AND gate. Clear to all of you? Next one, 14.12. Write the truth table for NAND gate connected as given in figure. So see, this is the NAND gate. How it is connected? So see, both the inputs of NAND gate are connected with each other. It implies that inputs are short circuited. Okay. Now see, first simply think about NAND gate. So input A, input B, then output that is not A and B, that is the NAND gate. 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. NAND ગેટ નું વર્કિંગ એન્ડ કરતા ઓપોઝિટ. ઓકે, તો આ આખું NAND ગેટ નું ટ્રુથ ટેબલ થયું. હવે તમને શું આપ્યું છે? તમને જો આ ઇનપુટ શોર્ટ સર્કિટ આપ્યા છે, તો એનો મતલબ એ થયો કે either both will be 0 or both will be 1. Now you will not get A0, B1 or A1, B0 because both inputs A and B are connected with each other. એટલે આ જે ચોઈસ છે આપણી 0, 1 અને આ 1, 0, આ ચોઈસ નીકળી ગઈ હવે. So now final truth table, that is input 0, output 1, input 1, output 0. So this is the working of NOT gate. So now we can conclude like this. The short circuited NAND gate behave as NOT gate. Clear? Now 14.13. You are given two circuits as shown in the figure, which consist of NAND gates. Identify the logic operation carried out by the two circuits. Okay? See, first this one. So NAND gate followed by short circuited NAND gate. So NAND gate, here output of the NAND gate, that is input of short circuited NAND, but we already proved this thing. Short circuited NAND behave as NOT. So see input AB 0, 0, 0, 1, 1, 0, 1, 1. So first this intermediate step, that is the output of first NAND gate, that is not A and B. So 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, sorry, 1, 1, 0. Now it is followed by short circuited NAND, it behave as not. So this output of the NAND, that is the input of not. So 1, so output will be 0, 1, output 0, 1, output 0, 0, output 1. Clear? So see here, now resultantly what happened? Input 0, 0, output 0. Input 0, 1, output 0. Input 1 0, output 0. Input 1 1, output 1. This is the working of AND gate. So we can say first circuit behave as AND gate. Now second circuit. In second circuit, first two short circuited NAND gates are given to you. So here we can say this thing, these two NAND gates will behave as not, because both are short circuited in input. So here take A, B input 0 0 0 1 1 0 1 1. Now short circuited NAND behave as not. એટલે આ ફર્સ્ટ ઉપરનો જે NAND ગેટ છે જે એ ટર્મિનલ સાથે છે, રાઈટ? તો એનો આઉટપુટ નોટ એ અને બીજાનો આઉટપુટ નોટ બી. તો હવે ઇન્ટરમીડિયેટ સ્ટેપ અહીંયા ટ્રુથ ટેબલમાં ઇન્ક્લુડ કરો નોટ એ નોટ બી. So this 0 to this one, this 0 to this one, 1 to 0, 1 to 0. Then for B, 0 to 1, 1 to 0, 0 to 1, 1 to 0. Clear? Now, these not A and not B are the inputs of NAND gate. But NAND gate that is made by and then after not. So, here first the working of AND gate. So not A and not B. So here see, both the inputs are present, 1 1, so you will get output. Then in any other case, 1 0 0 0 1 0 0 0 0. But after AND there is not in NAND gate. So now this will invert. So input 1, output 0, input 0, 1, input 0, output 1, input 0, output 1. Now forget about the intermediate steps. Now finally think about input 0, 0, then output 0. Input 0, 1, output 1. Input 1, 0, again output 1. Input 1, 1, output 1. This is the working of OR gate. So this particular given circuit in figure B that behave as OR gate. Clear to all of you? 14.14. Write the truth table for circuit given in figure below consisting of NOR gates and identify the logic operation which this circuit is performing. Now see this first circuit, this one given to you. NOR gate, then after NOR gate, but the second NOR gate is short circuited. See here, first consider the short circuited NOR gate. Its truth table A, B, 0, 0, output 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. But when two inputs are short circuited, then 0, 1, 1, 0, this choice is not possible. So resultantly, we will get 0, 0, 1, 1, 0. It implies that short-circuited NOR gate again behave as NOT gate. Now, we can prepare this particular circuit here with its equivalent circuit. So NOR gate as it is, but this short-circuited NOR is replaced by NOT because it behave as NOT. Now see, input A, B. Then for this first NOR gate, first in NOR gate is OR and then after NOT will be there. So first intermediate step, A or B, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Then after there is NOT. So not A or B. So 0 to 1, 1 to 0, 1 to 0, 1 to 0. Now, this particular output of NOR gate. That is the input of NOT. So NOT is inverter. So 1 to 0, 0 to 1, 0 to 1, 0 to 1. It implies that resultantly inputs 0, 0, output 0, 0, 1, output 1, 1, 0, output 1, 1, 1, output 1. It implies that this particular given circuit behave as OR gate. Clear? 14.15. Write the truth table for the circuits given in figure consisting of NOR gates only. Identify the logic operation or and not performed by the two circuits. Here in circuit A, short circuited NOR gate is given to you, and then this is second circuit. Actually, see, in previous example, we already proved this thing. Short circuited NOR gate behave as NOT gate. So see here, short circuited NOR gate that behave as a NOT gate. So here the truth table that will be 0, 0, 1, 1, 1, 0. Simple thing. This choice that you have to discard because both the inputs are short circuited. Then for second one, the truth table. So here A, B inputs of short circuited NOR gates which behave as NOT gate. So output of this first one that is not A, output of second one that is not B, and this not A and not B are input of NOR gate. So see intermediate steps. A, B, 0, 0, 0, 1, 1, 0, 1, 1. So not A, that is 0 to 1, 0 to 1, 1 to 0, 1 to 0. Then for B, 0 to 1, 1 to 0, 0 to 1, 1 to 0. And then after OR is there. Okay. And then after not will be there. So 1, 1 will be 1. અહીંયા એક step લખવાનું રહી ગયું. 1, 1, 1. But after that, not is there. So 0. Then 1, 0. OR gate will give you 1. But then after not will give you 0. Then after 0, 1. OR will give you 1. But then after not will give you 0. Then 0, 0. Your OR will give you 0. But after that, not is there, which will give you 1. It implies that. Now think about the inputs and final output. See 0, 0, and this output 0. 0, 1, output 0. 1, 0, output 0. 1, 1, output 1. It implies that this is second circuit given to you in figure B that behave as AND gate. Clear? Chapter is completed.